Okay, in this video we are going to go over the basics of Proton NMR. There are really four key things you need to know to understand and interpret NMR spectrum. Our goals are really to be able to predict an NMR spectrum from an organic structure or use an NMR spectrum to generate an organic structure. Again, four key things we need to know. So in this video we're going to go over these four items. Number one is the number of signals in your spectrum. That represents the number of non-equivalent hydrogen atoms. Number two, chemical shift, that's in ppm, gives you information about the environment around the hydrogen atoms, specifically what atoms are attached one or two bonds away to the hydrogen atom. Three is the integral of the signals. It gives you the ratio of the number of hydrogens represented by the signal. And four is the splitting pattern. It tells you the number of neighboring hydrogen atoms that are 3 bonds away. So in this video we're going to go through all four of these aspects. Again, we're looking at Proton NMR. Carbon-13 NMR is a little different. You don't need to know all of these four aspects for it, but this video is really focused on Proton NMR. So before we sort of get started on these aspects, let's just look at a typical spectrum. I want to point out a few things here. This is a typical spectrum. The first thing you'll see is our x-axis is a ppm scale. This is the chemical shift. The values are usually from 0 to 11. We can get information about our molecule really by looking at the spectrum. So here's the spectrum here. Or you can be given this data in the version of a table. Alright, so in this example I've really given you both. We have the spectrum, or we also have a little table that shows the exact same data. So going through this, we can see that there are 3 signals here. 1, 2, and 3. And those same signals are represented in our table 1, 2, and 3. The key things we need to know are the number of signals, the chemical shift, that's where the peak comes. So you see peak 1 comes a little bit, approximately 3.4, and we can see at our table that's listed as 3.4. Peak 2, the center of those, signal 2, the center of all of those peaks comes at 1.87. That's shown here. And then the third signal comes just at about 1, and in our table that's 1.03. We need to understand how many peaks there are in each signal. So if you look at the spectrum, it's a little hard to see, it's not as clear, but there's 3 peaks shown here, and that's indicated in our table by the term triplet. That means there's 3 peaks in signal number 1. For signal number 2, okay, there's a lot of peaks here, and if you count those, you can see that we have 6 peaks. That's called a sextet. And in signal 3, here again we have 3 peaks in our signal. That's called a triplet. The other information we need to know is the integral, and that value is given here in the table. It's 2, 2, and 3. In your spectrum, usually that's something that would be given on the table, so you might see something next to the peak where it would say 2H, 2H, and then a 3H, sort of indicating the integral value. Okay? So this is really the way NMR spectrum are really presented to students. And what you can see here is this is a spectrum of bromopropane, 1-bromopropane, and again, what we're trying to learn in this video is either to be able to predict the NMR spectrum from the structure, or from the spectrum able to predict the structure. So let's go through sort of the four aspects one by one so we're able to understand this a little bit better. Again, so here is the information, the four key things. First thing we're going to do is we're going to start with the number, we're going to start with the number of signals. So that's going to be the first thing that we're going to look at. So let's take a look at this information. So the number of signals represents the number of non-equivalent hydrogen atoms. So what does that mean? Well, let's first talk about what equivalent hydrogen atoms are. Equivalent hydrogen atoms are hydrogen atoms that are attached really to the same carbon. So if we look at our first example here, we see we have a methyl ketone on one side, which means there are 3 hydrogens connected to that carbon. All 3 of these hydrogens are equivalent because they're all connected to the same carbon. As we go through, this molecule doesn't have any symmetry. We can now draw in, again on the other side of the carbonyl, 2 more equivalent hydrogens in blue, another 2 more equivalent hydrogens in orange, and then finally at the end we have a methyl group where we have 3 hydrogens that I've drawn in purple. So in this first example, we have 1, 2, 3, 4 sets of non-equivalent hydrogen atoms, which means that this compound here would have 4 signals in its NMR spectrum. Let's go through and look through a couple more examples. Here's another example here. So here we have a ether. On the right side we have 3 hydrogens. Those are all equivalent, so they're all red. A new set of signals in blue. 2 more hydrogens in orange, and then another 3 in purple. So again, so far what we see is I have 3 equivalent hydrogens in red, 2 equivalent hydrogens in blue, 2 in orange, and 3 in purple. That gets us, again, 4 different non-equivalent hydrogen atom sets. So our spectrum would contain 4 signals. There's 4 non-equivalent hydrogens in this structure. If we look at the next compound of interest, here we have an ether, diethyl ether in fact, and we can see that this molecule is symmetric. So once we start talking about symmetry, the situation changes a little bit. Because this molecule is symmetric, I can draw a line of symmetry between it. The left side is exactly the same as the right side. What that means is that on the right side I have 2 hydrogens that are in red, that the hydrogens in red are equivalent to each other. Then I have 3 more hydrogens in blue. Those are equivalent to each other, but non-equivalent to the red. So the blue is non-equivalent to the red. But if we look at the left side, that's exactly the same as the right. So what that means are the 2 hydrogens on the left in red are equivalent to the hydrogens on the right. So because of this line of symmetry, this molecule here, in fact, is only going to show 2 signals instead of 4. And that's really the thing we have to remember about this, is because these hydrogens are in the same environment, this hydrogen in red is connected to a carbon, which is connected to an O and then a methyl. That's the exact same environment as the other side. So this is symmetric, so we only have 2 sets of non-equivalent hydrogen atoms. Our spectrum would only show 2 different signals. Looking at our next example here, again we'll start on the right. Notice we have 2 methyl groups connected to this same carbon I'm putting a dot on. well, those hydrogens are equivalent with each other. So we always have to look for these, for the symmetry in our molecules. Because these two methyl groups, I have an H connected to a carbon, H connected to carbon, because those are connected to the same carbon, these hydrogens in red are all equivalent with each other. So that will only show up as one signal. As we go through, we have another non-equivalent, now just one hydrogen on that black carbon. Two more in orange. Two more in purple. Two more in green. And then the last set here, I'm running out of colors, so we'll just set these in black. So if we look at this molecule, we have red, blue, orange, purple, green, and black. 1, 2, 3, 4, 5, 6. So this molecule will have 6 signals in its spectrum. Again, the reds are equivalent because the hydrogens are attached to a carbon which is connected to the same carbon. Blue H, orange, purple, green, and black. That gives us a total of 6 signals. So symmetry is very important when determining the number of non-equivalent hydrogens. If we look at our example of toluene, what we can see again is we have symmetry. So the left side of the molecule is going to be identical to the right side. So let's draw in our hydrogens. Let's not forget the methyl group. Those are equivalent. The 3 H's in red are equivalent. Then we have H's on the right. 1 H. That is equivalent to the H on the left. Same as we move down. And then at the bottom, another H. So if we count these, 1, 2, 3, 4, toluene will have a spectrum that has 4 signals in it. And another example here, again we can look at symmetry elements. Now this molecule is symmetric in 2 different directions. So if we draw in our hydrogens again, here's our methyl in red, and we have a hydrogen in blue. So this molecule will only have 2 signals show up in the spectrum. Alright, so all of these hydrogens here in blue are equivalent. All of the hydrogens on the aromatic ring are in fact equivalent. And then the hydrogens in red are also equivalent with each other. So we only have 2 colors, and therefore 2 signals. All right. Next, number 2. The next thing we want to look at is the position of these signals. That's called the chemical shift. This gives you information about the environment around the hydrogen atoms. What are the hydrogen atoms attached to? And typically your textbook or your instructor will really give you a table that describes this. Characteristic proton NMR chemical shifts. And what you can look from this table is it gives you a value in ppm, in parts per million, on where that signal should come. So if you have an H connected to a carbon to an R group, that's 0.9. And we can look at this table here. I'm not a big fan of this table. This is the table I think that comes from the textbook that I use. So what I've done here is I've really sort of created my own table that does a better job summarizing this. So here is the textbook here's the table in the textbook on the left, and now I've added my table on the right. So what I want to do is just kind of go through and convert these as we look, if I look at the first set of signals on the table, I see I have a methyl group at methyl 0.9. Then we see we have a value, so we have 0.9, 1.3, 1.5, 1.5 to 2. So I've really summarized this as these are basically, I'm going to call our first set of signals that we need to be aware of. And I'm putting a 1 here, and we're going to put that number 1 over here. What that represents is any time you have a hydrogen connected to an sp3 hybridized carbon, which is then connected to other sp3 hybridized carbons or hydrogens, our chemical shift values are going to be 0.8 to 1.8. All right? And this is sort of our baseline standard. So if you look at the table provided here, they kind of give specific examples. What we have to remember about our chemical shift is this is a generic range. It's possible to have values of 0.75. It's possible to have values of 1.9. But 90% of the signals you're going to see are between 0.8 and 1.8. So I'm talking about the hydrogen shown in red. When that's connected to an sp3 hybridized carbon, which is then connected to other sp3 hybridized carbons or hydrogens, your value will be 0.8 to 1.8. So if you see here, I'm saying R is sp3 carbon to H, or simply hydrogens. And I have a couple of examples of here. Here are some examples. All of the hydrogens shown in red would have chemical shift values of 0.8 to 1.8. So you'll notice in the molecule on the right, these two hydrogens would be 0.8 to 1.8. Same with this methyl group. The hydrogens here and at the end would not. They would have a different value. Next, looking at our table, I like to group the next set into what I call 2. And what do these all have in common? I have a H connected to an sp3 carbon connected to an sp2. H to sp3 to sp2. H to sp3 carbon to sp2. And that is going to be the second row in my table. So if we look, if I have a hydrogen that's connected to an sp3 carbon, and that sp3 carbon is connected to an sp2 carbon, this hydrogen in red will have a chemical shift of 2 to 3 ppm. It'll come somewhere in that region. So let's look at a couple examples we have here. So if you look at this molecule here, we have a ketone. On the carbon to the right, there's 2 hydrogens there. Those hydrogens would have a chemical shift of anywhere between 2 and 3. So I have the H I'm talking about in red connected to an sp3 hybridized carbon, which is then connected to an sp2. We see the same example here with our alkene, H to sp3 to sp2, or toluene, H connected to sp3 to sp2. So what you have to notice for these values, I'm looking at the hydrogen connected to an sp3, and then what is that sp3 carbon attached to? Just other sp3 carbons to H's, 0.8 to 1.8. If it's H to sp3 to sp2 carbon, that's now 2 to 3. And you can see these examples here. As we go through our table, I'd like to just point out in here, I left this off mine. It's not as common, but if you happen to have an alkyne, a hydrogen attached to an sp hybridized carbon, that's going to have a value of 2.5. All right? So you definitely should be aware of that value, but it's not as common. Next on our list, we have H connected to carbon connected to N. That has a value of 2 to 3, and that's the third thing on my list, on my table. And we can see that here. H connected to sp3 carbon connected to N. That should have a chemical shift of between 2 and 3 ppm, and you can see our example here, H to sp3 to N. All right. Notice there's hydrogens here. Those are not 2 to 3. That would fall into this category of 0.8 to 1.8. Right, so I'm just talking about the hydrogens in red. As we continue on, sort of looking at the generic table, next we see H to carbon to halogen, Cl, Br, or I. The table here lists 3.5, and that's the next row in my table here. And generally what we find, this value of 3.5 is a little too specific. Again, we should have a chemical shift of between approximately 3 to 4 ppm. So when I have a hydrogen connected to an sp3 carbon, and that sp3 carbon is connected to a halogen, that chemical shift will be anywhere between 3 and 4 ppm. So we can see that in an example here, H to sp3 to Br, 3 to 4. Next on our chart, a very important one, H to C to O. This is the fifth row. That's shown in the table here. So let's look at how I demonstrate this. Number 5. Now I'm talking about a hydrogen connected to an sp3 carbon, and that sp3 carbon is attached to an oxygen. Those hydrogens are going to have, again, a chemical shift of about 3 to 4. So we can look here, if we have propanol, H to sp3 carbon to O, the hydrogens in red would be between 3 and 4. Here I have an ester, right? The carbon, the H is in red, connected to the carbon, connected to an O, again would have a chemical shift of 3 to 4. Now we're going to change gears a little bit. If you notice all of the examples, 1 through 5, I'm looking at hydrogen connected to sp3 carbon connected to something else, sp2, N, X, OR. Now we're going to be talking about hydrogens connected to sp2 carbons themselves. So next in our example, H to sp2, H to sp2. This is the 6th row in my table. And we can clearly see here I'm talking about a hydrogen now directly attached to an sp2 hybridized carbon. And when I say carbon sp2 hybridized, I'm not talking about an aromatic ring. I'm talking specifically about an alkene. So when you have a hydrogen connected to an sp2 hybridized carbon of an alkene, that will have a chemical shift of approximately 5 to 6. And that's what we see here. So here's an example. H's connected to sp2 hybridized carbons will have chemical shifts of 5.6. Last on our table, very important again, hydrogens connected to aromatic rings. That's the 7th row in my table. Now we're talking about H to sp2 of an aromatic ring, and that's going to have a chemical shift of 6.5 to 8. And we can see that example here. Here we're looking at parabromoethylbenzene. There's 4 hydrogens here connected to this benzene ring. One note, the peaks in this range are usually overlapping. In a few slides we're going to be talking about splitting patterns. This can be very complex, so often we don't look at splitting when it comes to benzene rings. We can, but at a basic level you don't always have to. Final thing, looking at our table, if I'm looking at a hydrogen of an aldehyde, that can have a range of 9.5 to 11. I have left that off my table. Again, it's something you should be aware of. It's not as common. We're looking at the H of an aldehyde. Finally, what I want to do is I want to talk about the whole next set here, because these are different. I'm marking these in green. Now we're talking about hydrogens connected to heteroatoms. H to an N, H to N. Right? H to O of an alcohol, H to O of a phenol, H of a carboxylic acid. These have very specific ranges, and this is a good example where you want to use that table. Amines will come from 1 to 3. Aromatic amines 3 to 5. Amides 5 to 9. Alcohols 1 to 5. Phenols 4 to 7, carboxylic acids 10 to 13. So here's an example where the tables are very effective. All right. So I've really listed all of these, sorry, not as 7, but as 8 on my table, and I just want to mention that here. And basically what I say is this, all right, is that the hydrogen connected to an O or an N are usually variable depending on the functional group. Here's where the table is very effective. Some other things that are very important. These peaks are usually very broad, and they're singlets, so there's no splitting. So when we talk about splitting, you'll notice there are no splitting patterns typically observed for H to O or H to N. The other thing is, besides seeing that the peaks are broad or singlets, sometimes instructors will give little hints to remind you that this is an H on an N or an O, and sometimes those are labeled as D2O exchangeable. So if we remember, hydrogen is visible in an NMR spectrum. Deuterium, because it has an even spin, is not. So deuterium you will not see show up in an NMR spectrum, and we call that D2O exchangeable because the H on the heteroatom, the H on the O or the N can be exchanged with D, which is invisible in the NMR. Okay, so this table is very important for you to understand and be comfortable predicting or understanding the chemical shifts. And I think my table does a very good job of sort of summarizing this quite effectively. Alright, so let's see if we can put this to use a little bit. What I want to do is just predict where the signals will appear, what the chemical shift will be. So we're going to sort of go through the same exercise we did before. I'm going to label the equivalent and non-equivalent hydrogens. So here we have a set in red, a set in blue. This molecule is not symmetric, so we have another set of non-equivalent hydrogens in orange and then purple. Okay, so this structure would show 4 signals in the NMR. Where do those come? So let's look at the signals in red here. Here I have an H connected to an sp3 carbon to another sp3 carbon. Where does that show? That's our base value of 0.8 to 1.8. Alright, so what I'm going to do here is just list 0.8 to 1.8. So our signal would come anywhere in that range. Next, let's look at the hydrogens in blue. H connected to sp3 carbon. To the right is sp3 carbon, but to the left is an sp2 carbon. So where does that show up here? H to sp3 to sp2. So our signals in blue, these hydrogens would come, the signal would come somewhere in the 2 to 3 ppm range. As we look now at the hydrogens in red, H to sp3 carbon. One side is another sp3 carbon. That's sort of our baseline. We don't need to do anything there. I look at the other side, H to sp3 carbon to oxygen. Where does that come on our table? Right here, H to sp3 to O. So those peaks in orange would have a chemical shift of anywhere between 3 and 4 ppm. And then finally, we're looking at purple. Again, purple is H to sp3 to sp3. That's our base range. That's going to come at a value of approximately 0.8 to 1.8. Alright. If we look at our next molecule, I'm just going to erase a little bit here so I have a little more space. Let's look at our hydrogens here. Okay, we have two hydrogens on our alkene. Technically, these 2 hydrogens are non-equivalent. That's sort of an advanced topic because the hydrogen here is cis to that hydrogen and trans to the ring. But right now, we're just focusing on chemical shifts, so let's leave it at that. Alright, we'll draw a hydrogen in blue, 2 in orange, and another 3 in purple. So again, in here we would have 4 signals in our spectrum. Where do these values come from, or what are the chemical shift values? H to sp2 hybridized carbon of an alkene. Where does that land? Right here, 5 and 6. Again, if we look at blue, H to sp2 carbon, again, that's a 5 to 6 range. So our hydrogens in red would come between 5 and 6. The hydrogens in blue would also come between 5 and 6. Looking at the hydrogens in orange, H to sp3 sp3 on one side, sp2 on the other. Where does that land? H to sp3 to sp2. So our value in orange would have a chemical shift of approximately 2 to 3 ppm. And then obviously if you look at the one in purple, H to sp3, carbon to sp3. That's sort of our base region. We're looking at, again, 0.8 to 1.8. So our signal would come in that range. Great, let's look at our last example here. So we're going to fill in all of our hydrogens. I'll start with my ethyl group. We have 2 hydrogens there in red. We have 3 hydrogens at the end. I've got another methyl connected to an O, and then we have some aromatic hydrogens here as well. So we'll add H, green. I need to reuse my colors again, so we'll do a second one in red and a second one in blue. So I just want to make a little bit of a note. Let me just give myself a little more space here about our benzene ring. So technically, we would see 1, 2, 3, 4, 5, 6, 7 signals in our NMR spectrum. 1, 2, 3, 4, 5, 6, 7. Right? There's no symmetry in this molecule. This is an ethyl, this is a methoxy. There's no symmetry here, so technically we would see 7 different signals. All right. The problem with the hydrogens attached to the benzene ring is typically they are overlapping. All right. So from a basic understanding, we can almost treat these as one signal. So what I'm going to do is, you should understand that there are 7 signals that you can see, but what I'm going to do is I'm going to treat all of those the same. So even though technically they're different, we're going to treat them all as the same, because the peaks are generally overlapping in the aromatic region anyway. So let's take a look. I think we started with red first. In red, I have H to sp3, sp3 on that side, sp2 on the other. Where does that land? Right here. So that will have a range of 2 to 3. The one in blue is just our normal situation, 0.8 to 1.8 chemical shift. The hydrogen in orange is an H connected to a carbon to an O, HCO. That has a value of between 3 and 4, so our signal will appear between 3 and 4 ppm. And then again, there are technically 4 different signals in the aromatic region, but I'm going to lump them all together. These are all hydrogens connected to a benzene ring, 1, 2, 3, 4, and that will have a value of 6.5 to 8. So technically that composes 4 different signals, but because there's so much overlap, we can really lump them all together. Next, we're going to look at the integral of the signals, the ratio of the number of hydrogens that are represented. This is very, very simple. So if we look at our first example, we have a CH3, 2 H's here, 2 H's here, and 3 here. So the number of 1, 2, 3, 4, 4 non-equivalent. We'll see 4 signals in here. What is the integral ratio? That's simply the number of hydrogens represented by the signal. We have to remember that this is always a ratio, but it's quite easy to see. Our ratio would be 3 to 2 to 2 to 3. Why? There's 3 hydrogens represented by that signal, 2 by that signal, 2 here, and 3 there. As we go through our examples, I'm not even going to draw in my hydrogens. This molecule here is not symmetric, right? A methyl group with 3 to 2 to 2 to 3. Okay? So again, our integral ratio, this signal here is represented by 3 hydrogens, 2 to 2 to 3. Let's look at diethyl ether. If you remember, we already talked about the fact that this is symmetric. So we represented, we looked at this molecule was symmetric. So we said that there are only two signals shown, one in red and one in blue, and the left side exactly matches that of the right side. So we can draw that in. Okay. So when we look at the ratio of peaks, here I can see I have 1, 2, 3, 4, 5, 6 hydrogens in blue, 1, 2, 3, 4 hydrogens in red. So overall our ratio would be 6 to 4. Right? But remember, this is always a ratio, so this can be represented by 6 or 4, or more realistically, we'd give the least common factor here and represent this ratio by 3 to 2. Okay? So it's possible to show that the ratio is 6 to 4. Most likely this would be represented that we have a ratio of 3 to 2, sort of representing the ratio there. If we look at our final example, let's draw in our hydrogens. 2 in red, 3 in blue, 3 in orange, and then I did purple, green, we'll do another red and another blue. Okay, so again, we talked about this example before. There's technically 7 signals here. 1, 2, 3, 4, 5, 6, 7. And we can see our ratio is 2 to 3 to 3 to 1 to 1 to 1 to 1. 2 to 3 to 3 to 1 to 1 to 1 to 1. But, as we mentioned before, often the hydrogens of the aromatic rings overlap. So many times it's hard to tell which peak belongs to which hydrogen. And guess what? That's fine. Because these hydrogens all will come between 6.5 and 8, the hydrogens in black, we can just integrate and lump them all together. So many times you'll see sort of a ratio provided where all of those aromatic hydrogens are lumped together. That would give me a ratio of 4 aromatics to 2 to 3 to 3. Okay? So you have to be aware that sometimes all of the aromatic H's will be lumped together. And if that's the case, we'd have a ratio of 2 to 3 to 3 to 4 for all the hydrogens that are in the aromatic region. Last thing we need to discuss is the splitting pattern. Okay? And this is really the most complex aspect of this. The splitting pattern tells us the number of hydrogens that are 3 bonds away. So let's draw in our hydrogens again. Red, 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 blue, orange, and purple. Okay, so this molecule will have 4 signals. We've already talked about the number of signals, we've talked about chemical shift, we've talked about the integral ratio. Now splitting pattern. Splitting pattern is what is most powerful about NMR, because when I look at the signal in red or the signal in blue, I get information about the hydrogens that are next to it. The hydrogens that are next to it. So we're always looking for things that are 3 bonds away. As we do this, I just want to introduce a little bit of terminology here. If we have 1 peak, we call that a singlet, and that's abbreviated with an S. If your signal is broken into 2 peaks, that's called a doublet and abbreviated with AD. If your signal is comprised of 3 peaks, that is a triplet, abbreviated with a T. 4 is called a quartet, abbreviated with a Q. As we go down, 5 peaks is a quintet. 6 peaks is a sextet. 7 is a septet. Right, and anything greater than that, we usually use M for multiplet, and that means we have a lot. All right, so bear in mind, I'm going to sort of be using these terms: singlet, and I'll write an S, doublet, D, triplet, quartet, quintet, sextet, septet, or multiplet, which means it's quite complex. Singlet 1 peak, doublet 2, triplet 3, quartet 4, quintet 5, sextet 6, septet 7, multiple many peaks. All right. So let's just make sure we have plenty of room and we can remember those terms. So what I'm doing, let's go back to our example here. I'm counting hydrogens that are non-equivalent and 3 bonds away. So if I look at this H in red, all of these hydrogens are equivalent. I just pick one. How many hydrogens are 3 bonds away? So here's 1 bond to the carbon, here's 2. How many hydrogens are attached to this carbon? 0. All right? And the rule is such. It's the number of neighbors plus 1 equals the number of peaks. N plus 1 equals the number of peaks, where N is really the number of neighbors. So, if we look at the signal in red, this has 0 neighbors. H to carbon 3. How many hydrogens are here? 0. So that means in red, this signal would be represented by 1 peak. Therefore, it would be a singlet. Let's look at blue. So I pick one of these hydrogens. How many hydrogens are 3 bonds away? There's 1 bond to that carbon. Here's 2. How many hydrogens are connected to this carbon? None. What about the other side? This H, 1 bond, 2. How many hydrogens are connected here? 2. So the signal for blue will be split into 3 peaks, or a triplet. And that's what we have to remember. Integral tells you the number of equivalent hydrogens within that signal. This has an integral of 2. The splitting pattern is a triplet because there are 2 neighbors. If we look at the orange, how many hydrogens are 3 bonds away? 1 bond, 2 bond. How many hydrogens are on the right? 2. How many hydrogens are on the left? 3. So there's 1, 2, 3, 4, 5 neighbors for this orange peak. 5 neighbors equals 6 peaks. The signal for the hydrogens in orange would be broken up into 6 peaks. That is called a sextet. If we look at purple, how many hydrogens are 3 bonds away? 1, 2. How many hydrogens are here? There are 2 hydrogens here. 2 neighbors plus 1. The signal for purple would be split into a triplet because there are 2 neighbors. And here's sort of the analogy I like to use. I like to think about hydrogens as sort of people living in a house. So here there are 3 hydrogens living in our house, and that house is our carbon. How many neighbors do you have? Well, here's a carbon. There's no hydrogens there. There's 0 neighbors, so it's 1 peak. If we look at blue, we have two people living in the house, in the carbon. How many neighbors are on the right? That's a house, but there's no neighbors. How many on the left? There's your carbon, which is a house, which has two neighbors. Two neighbors plus one. The hydrogen, the signal in blue, would be a triplet. What about here in orange? We have two people living in this house, this carbon. How many neighbors? On the right side, there's the house carbon that has two people living in it. On the left, here's the carbon that has three people living in it. There are 5 neighbors to this orange signal, which means that 5 neighbors plus 1 gets me 6 peaks, or a sextet. And here in purple we have 2 neighbors that are 3 bonds away, which means that signal is a triplet. Alright, let's go through more examples. We'll go through this a little bit faster. I'm just going to draw in all of the hydrogens. Here they are in red, 2 hydrogens in blue, 2 hydrogens in orange, and another 3 in purple. So let's go through. The hydrogens in red have 2 hydrogens that are 3 bonds away, 2 neighbors. So this peak in red would be split into a triplet. Hydrogens in blue, no neighbors on the right, 3 on the left. This would be split into a quartet, 4 peaks. On the right side, we're going to see exactly the same case. This hydrogen in red, sorry, the hydrogens in orange have 3 neighbors. That means that would be split into a quartet. And the hydrogens that in purple have 2 neighbors, that would be split into a triplet. And one thing you can see here, this is common for an ethyl group. We have a triplet and a quartet. Okay. The other examples we talked about, diethyl ether, we know that that's perfectly symmetric. Again, here we see an ethyl group, hydrogens in red and blue. The hydrogens in red, 2 hydrogens here, 3 neighbors. So the signal in red would be split into 4 peaks, which is a quartet. The hydrogens in blue would be split into 3 peaks, 2 neighbors plus 1, which is a triplet. Looking at our benzene ring example, all right, in this case, sort of on the basic model, we can sort of ignore splitting on our aromatic ring. Okay. Not always. But that's the basic way to handle this. So again, if we look at our examples here, for now, I think the basic thing is don't worry about splitting for the aromatic hydrogens. We're just going to look at the hydrogens in red. Have 3 neighbors, that would be a quartet. The hydrogens in blue have 2 neighbors, that would be a triplet. And if we look at orange, there are no neighbors over here, so that would be a singlet. Okay. One thing I want to mention is splitting patterns are very, very complex. This is a very basic level. And that's sort of why we're skipping talking about splitting at aromatic rings. It gets much more complex. When we talk about splitting patterns of alkenes, that also gets quite complex. So this is a basic and simple understanding of splitting patterns. Alright, for the last thing, let's put everything we just learned together. Let's focus on our 4 areas and see if we can predict the NMR spectrum for the following molecule. Alright, I have another follow-up video that really talks about how to interpret spectrum to draw a structure. That's a little more complicated. It just takes a little more practice. Right now, a good problem is to see if we can predict the spectrum of an actual molecule. So let's go through the steps that we've really worked on. First, let's figure out how many signals we're going to have. So what I see is we have 2 methyl groups attached to the same carbon. We know due to symmetry that these methyl groups are going to be equivalent, so that'll be our first signal. We'll put that in red. Next, a lot of students forget that there's a carbon that's sp3 hybridized. We do have a hydrogen there. We'll put that in blue. Followed by that, 2 hydrogens we have in orange. On the other side of the molecule, 2 more hydrogens in purple, and then finally finally 3 more hydrogens in green. Okay, so we can clearly see in this molecule we're going to have 1, 2, 3, 4, 5 different signals. I'm going to call these A, HB in blue, C in orange, HD in purple, and HE in green. So we can sort of put these down here. A is in red, B is blue, C is orange, D is purple, and E is green. Alright, so let's walk through and figure out our table. We have the number of signals. We want to do chemical shift, integral, and splitting pattern, the number of peaks we see. So let's first work through A. A, chemical shift. Which one do I look at? Either, because they're equivalent. I have an H connected to an sp3 carbon to an sp3 carbon. What is my range for the chemical shift of that? Well, that is my normal situation, so I will have a peak from anywhere from 0.8 to 1.8 ppm. Okay? Why don't we do all our chemical shifts first? If I look at HB in blue, H to sp3 carbon, and what is that attached to? An sp3, an sp3, an sp3. Again, that is my normal situation. Nothing out of the ordinary. That gives me a range of 0.8 to 1.8 ppm. We look at chemical shift for HC in orange, H to sp3 hybridized carbon, sp3 hybridized carbon on the left, sp2 hybridized carbon on the right. So what does that mean? A chemical shift for our signal of HC in orange will come in a range of 2 to 3 ppm. Now we're going to look at HD, H to sp3 carbon, sp3 on the right, O on the left. Where does that come? H to sp3 to O comes between a range of 3 to 4. So this signal in purple will have a range of 3 to 4. And E, H to sp3 carbon to another sp3 carbon, that will show up also as our normal situation, 0.8 to 1.8. Good. Now let's look at the integral. What is the ratio of the peaks? This is quite easy. I just have to count how many equivalent hydrogens I have here. So how many do I have in red? 6. My ratio is 6. 1 in blue, 2 in orange, 2 in purple, and 3 in green. So my ratio is 6 to 1 to 2 to 2 to 3, 6 to 1 to 2 to 2 to 3. Again, very simple. Splitting pattern. I'll take H to sp3 carbon. How many neighboring away? I look at either one of these, not both. H to carbon, how many hydrogens are attached to the carbon next to it? Well, there's only one. So that means that this signal, if there's one neighbor, will be split into 2 peaks. That is going to be a doublet. If I look at the H in blue, 1 carbon, how many neighbors do I have? There's 3 here, 3 here, and 2 here. So there's going to be 8 neighbors that we have. So we don't have a name for this. but this is going to be split into 9 different lines. Remember, it's the number of neighbors plus 1. 3, 6, 8 neighbors plus 1, 9 lines. If we look at HC here, attached to this carbon, how many hydrogens are attached to the carbon to the right? 0. How many to the left? 1. So for C, again, we're going to see this signal will be a doublet for the 1H in blue. As we go to purple, 2 signals represented here. How many hydrogens 3 bonds away? There's none over here. There's 3 hydrogens, neighboring hydrogens on that side. We have to add 1 more. So our purple signal will be split into 4 peaks or a quartet. Finally, looking at our last signal, 1, 2, 3 hydrogens. There are 2 neighboring hydrogens that are 3 bonds away. So clearly this last peak will be split into a triplet. So this shows us a prediction of what our NMR spectrum would look like. Okay, so the last thing I want you to do is I want you to do exactly what I did, predict the spectrum for the following 2 molecules. So take this ester here, figure out how many signals you have, fill out the table, what the chemical shifts would be, the integral and the splitting pattern, and then do the same for structure B here. For the benzene ring, for our aromatic ring, you do not need to worry about splitting pattern, and you can group all of these hydrogens together. So when you're predicting the number of signals, 1, 2, 3, group all of these signals together, count them all as one signal.